Hey everybody, this is Mr. Copeland. Today we're going to learn about a phenomenon known as the Doppler Effect. And I can sum it up with just a noise, and you'll have to bear with me because this is going to sound kind of silly. But imagine you're out standing next to the street. There's a car moving very quickly, and it's moving, down the street towards you. You're going to hear a noise like as it goes past you, right? Sounds pretty high-pitched as it's moving towards you, and then much lower pitch as it's moving away from you. The reason that happens is, without getting too technical, basically, in front of the moving car or whatever it is, in this case we got a fire truck, those sound waves get bunched up really close together. Behind it, though, they can spread out much more. So if you're up here in front of the truck, you're going to hear more sound waves hit your ear, per second. So it's a higher frequency. And then if you're back here behind the truck, fewer waves per second, which is a lower frequency or a lower pitch. So let's take a quick look. This is our person. Let's say that this is you. We've got this fire truck heading towards you at 20 meters per second. We'll take a look at how to use the equation to figure out what frequency you would be hearing if you were right next to the road and the truck was coming your direction. So frequency of the listener, we don't know. We'll try to find that out. Let's say that the siren emits a frequency of 300 hertz. So if nobody was moving, the truck is sitting still and you're sitting still, you would hear 300 hertz. But because you're standing here in front of the truck, you're going to hear a higher pitch. And we can use the Doppler effect equation to calculate what pitch that would be. Okay, here is the Doppler effect equation. Let me go through these variables with you here. L stands for listener. S stands for source. So FL is the frequency that you would actually hear as the listener. Fs is the frequency that the source is actually emitting. So here in our example problem, you'll remember the frequency of the siren or the frequency of the source is 300, and you don't know your listener frequency yet. That's what we're trying to figure out. V stands for the speed of sound. And as I told you the other day, unless I specifically tell you otherwise, we're going to say that the speed of sound is 343 meters per second. Now, we know, like I just said, frequency of the source is 300 hertz. VL stands for listener velocity. So if the person listening is moving, then you'll have a number to plug in for VL. But in this case, we're not. We're standing still. So we're going to plug in 0 for VL. Now, here's where it gets a little trickier. What we need to figure out, we know the source, or the fire truck in this case, is moving 20 meters per second, but where this gets a little trickier is figuring out whether to make that number positive or negative in the equation. And unfortunately, this is a complicated concept. So here's how it breaks down. Follow along and just, like, it's not going to make perfect sense why the equation is written this way. I feel like there are definitely better ways they could have done it. But nonetheless, here we are. So here's what you need to know. If the source is moving toward the listener, we're going to say that the velocity of the source is negative. Does that make sense? Not really, but it's what we're working with, unfortunately. And then here's where it gets even worse. If listener is moving toward source, VL is positive. And that is frustrating, but that is the reality. So in this case, back to our example, the truck is moving toward the listener. So if the source is moving toward the listener, then our source velocity is negative. So we need to make sure, in this case, because the source is moving towards us, we got to make sure that we make our source velocity negative. Okay, I'm going to flip over to the next screen and work through the numbers with you. So just bear with me there. And as we said before, we're looking for a higher frequency because we're having all these sound waves bunched up and we're in front of the moving vehicle, so we're looking for a frequency higher than 300. Remember that as we work through it. All right, so here we are on the next screen. We're looking at the same equation. We're going to plug in our numbers and solve the example problem. All right, so we don't know the frequency of the listener. That's what we're trying to figure out. We always use 343 for the speed of sound, which is just the regular V by itself in this equation, unless the problem tells you otherwise. But usually it'll either be 343 or close enough to that it really doesn't make a difference. The listener is not moving. And as we said, doesn't make a lot of sense necessarily, but if the source is moving towards the listener, then you make the velocity of the source negative. So we subtract 20. All right, so you've got 343 over 323 times 300. And that equals, rounds to 319 hertz. So that's our answer. We're hearing a frequency that's about 19 hertz higher than the source frequency because the truck is moving towards us. So it's a concept we all pretty much understand already. It's an equation that's kind of annoying when you have to figure out positive and negative, but make sure you take good notes here on how to break down positive and negative so that you plug things into your equation right. All right, thanks everybody. You'll have a couple of homework problems that are posted today as well. Let me know what questions you have.